Speed and velocity. As we talked about in class today, speed is simply the distance you've traveled divided by the time interval during which you travel. Okay? And as an equation, V represents speed, and D represents distance, and T represents time. We often also will call the distance delta x. The Greek letter delta, this big triangle, means change in the value. So this delta x means the change in the value of x, change in position, divided by time, gives us the velocity. The more your position changes in a given amount of time, the faster you're moving, the faster your speed. The only difference between velocity and speed is that velocity has direction. It's speed and direction. So speed is a scalar quantity. It's just got a magnitude or a size. You're traveling so fast with nothing about its direction, whereas velocity is a vector. It has a magnitude, which is the speed, and a direction. And the reason we make that distinction between speed and velocity links back to that idea of equilibrium that we talked about in the previous chapters. In the equilibrium rule, the sum of all forces, sigma F, equals 0. And if you're in equilibrium, then there's no change in your velocity. And of course, built into the fact that your velocity is not changing is the fact that your speed isn't changing. But in addition to that, no change in velocity also means no change in direction. And if you remember the trip we took in the elevator, whenever your speed changed in the elevator, you felt the force that caused that change. Either you were squashed into the elevator or you felt that lightness. Whenever you weren't in equilibrium, you could feel the force that caused it. And you'd feel the same thing if you changed direction. If you're driving in a car and you turn a corner, then you feel a push to the outside of the car. You're feeling the force that's causing you to change direction. And so we make that definition of velocity because forces can change either your speed or your direction. They change your velocity. Okay, and we'll do more on that as we get into chapter 6 later on. Another important distinction we want to make, other than between speed and velocity, is between instantaneous speed and average speed, or instantaneous velocity and average velocity. So as we discussed in the experiment today, the average speed, AVG for average, is just the distance you've traveled divided by the time it took. And if you look at the graph that you plotted of distance versus time, which should look something like this, with a clear upward slope, not a straight line. If a ball travels, let's say, 0.8 meters, so we can go across, read across to a point on the graph here, and then read down to find out what the time was, and it's about 2 seconds. Then, if we're calculating d over t, we're calculating this distance, the rise of the graph, and we're dividing it by this distance, the run of the graph. So, if we plot distance versus time, what we're actually calculating is the slope of the straight line that joins these 2 points. So, the slope of this line that joins this point to this point is giving me the average speed over that time interval. If I change the color of my pen, let's pick red. If I were to calculate the same thing for this time interval from 0 to almost 2.5 seconds, then the rise is about 1.2 up there, the run is about 2.4. The line that joins those 2 dots is like so. The slope of the red line is not the same as the slope of the white line. The average velocity over those 2 different time intervals is not the same. The slope of the red line is greater. The average velocity over that longer time period was actually higher, which reflects the fact that it's going faster and faster. So if I want to calculate the average speed over any time interval, if I just tidy this up a little bit, all I've got to do is draw a line connecting one point on my graph to another point on my graph, join them up, and calculate the rise over the run. And in this case, I've calculated the average speed between about maybe that's about 1.2 seconds, and here a little under 2 seconds. And the slope of that line again would give me the average speed over that time interval. But the instantaneous speed is the speed at any point on its travels. And in order to narrow down to that, I would have to take the slope of a line connecting smaller and smaller points. And it's never going to be the same as the average velocity. So the average speed is just distance over time, delta x over t, where t is a time interval, the time during which this change in position took place. So it's speed measured over an interval of time, whereas the instantaneous speed, v inst, is the velocity at an instant in time, at a particular point in time. So if your velocity is changing all the time, distance over time for a given distance will give you the average velocity during that whole time interval while it was traveling. The instantaneous velocity is how fast it's traveling at any particular time. If you're driving in a car and you're looking at the dashboard, the speedometer, the needle, is showing you how fast you're going at that time, at that instant. It's giving you the instantaneous speed. If you were to drive around for a while and look at the change in the odometer reading, the distance you'd actually traveled, and divide that by the time for which you were driving around, then you would have an average speed over that time interval. And the two wouldn't be the same. It's 200 miles to New York from Severna Park, give or take. If you did that in 2 hours, that's a pretty fast average speed of 100 miles an hour. But you couldn't guarantee that anyone was traveling at 100 miles an hour at any particular point on that trip. All you would know from the distance and the time is the average speed for the whole trip.